Right, we are discussing the Friedmann solutions, or rather we are on our way to derive the Friedmann equations and then to discuss the Friedmann solutions. For that purpose, we write the Robertson-Walker metric in the form where the k occurs explicitly. That's more convenient for solving the field equations. So not the form with a chi, but either the form with a eta or with a rho. I've chosen the one with the eta. The omega squared is the angular part, the theta squared plus sine squared theta d phi squared. And I had already written down on the board the components of the Ricci tensor. I'm afraid I have to do it again, at least some of them. So? Yeah, thank you. Okay, now I think it's correct. Okay, so you calculate the Ricci tensor, or rather you let a computer program do the work for you. And to get a TT component, that's fairly short, minus 3 A of t. And please, for the purpose of this lecture, when I do it on the board, allow me to write a prime for the derivative. Most books you could use a dot. I deliberately do not use a dot because I want to reserve the dot for derivative with respect to curve parameters, which occurs quite frequently. So in the written version, I write always d by dt, so then it's clear what I mean. But here on the board, just to save a little bit of time, allow me to denote it by a prime. And then we have an eta-eta component. The eta-eta component was 1 over 1 minus k eta squared, and then terms with derivatives of a 2k plus 2 over c squared a prime of t squared plus a of t over c squared and the second derivative of t. Okay, and the other ones, the remaining components, and you calculate r theta theta and r phi phi, and you see that the same term occurs again. So you can combine the other equations in the following way. R phi phi is sine squared theta r theta theta, and this is proportional to this here. So I can write it in this way. This factor is not there, so I have to multiply everything with this, and then I think it's an eta squared. Yes, eta squared. R eta eta. Yeah, so if you insert this expression for r eta eta, then you can read the r phi phi and the r theta theta, and the mixed components are 0 for nu different from nu. So these are the components of the Ricci tensor. And of course, we want to solve Einstein's field equation. So we want to solve the equation r mu nu minus r half g mu nu plus lambda g mu nu is kappa t mu nu. And as always, we have to specify what the energy momentum tensor should be. And as a trial, we do it with a perfect fluid. And then let's see what will come out, if it works or if it does not work. So we assume that our energy momentum tensor is, oh no, that's not the spelling. Perfect fluid. So there's a mass density, a rest energy density. Actually, the units of these things are mass per volume. That's the way I usually write it. So the rest energy density would be mu times c squared. Yeah? P over c squared, u mu u nu. That's the fall velocity of the fluid, plus p g mu nu. And let's try it with the simplest form of the fall velocity, namely, we have the Robertson-Walker universe, namely, let's try if it works with a fluid moving with a standard observers. Yeah? So that the fluid flow is perpendicular to the slices t equal constant. So that would mean that the u with the upper index is just delta mu t, yeah? It has only a t component, and actually the factor has to be determined by the normalization condition, but as we have here the just the minus c squared, which we want to have, there's no factor here, right? And then if we pull the index, here we have the u with the index down. So u mu is then, or let me write u mu. This is then, of course, g nu mu, u mu. And if I insert the Kronecker here, we see that this is just g nu t. So it is minus c squared if nu is t, and it is 0 otherwise, right? Because there are no mixed components, no g eta t or g theta t or something like that. Okay, and then let's insert this into the I forgot to write the Ricci tensor, sorry, the Ricci scalar. We also need the Ricci scalar. So I've written the components. Here I need the Ricci scalar, right? I also have to calculate this. So actually this should have been written here. So let me try to squeeze it here. Oops. The Ricci scalar. So this is calculated from these components, right? You take the trace with the metric, you invert the metric, which is easy because it's diagonal. You calculate the Ricci scalar, and then you get 6 over c squared a of t squared c squared k plus a prime of t squared plus a of t. Second derivative. Yes, that's it. Okay. So this gives us the left-hand side. Here are all the components of the Ricci tensor, the Ricci scalar, and the metric is written up there. And now we have specified the right-hand side. We want to try it with a perfect fluid. So we have to calculate the components of these things. So TTT is what? TTT is mu plus p over c squared. And then I have now the index is t, so I have gtt squared. Yeah? Gtt squared plus p gtt. And what is gtt? Gtt is minus c squared. So this is mu plus pc squared. The minus sign goes away because of the square, and then it's c to the 4. This is minus c squared. And yes, fortunately, the signs are correct. So the p cancels, and we just get u c to the 4. So that's, from this equation, we can read that it's correct what I said, that mu is the rest mass density, as the rest energy density, right, up to a factor c squared. Because our fluid is at rest on the t line, so TTT gives the energy density with respect to this vector field, and this is up to the dimensional factor indeed given by mu. Then we have T eta eta. So T eta eta, this is 0, this is 0. So I just have the last term, P G eta eta. And G eta eta, where is eta here? This is A of t squared divided by this denominator. Oops. 1 minus k eta squared. And then we have the analogous expressions for the other elements. So this contains a d theta squared, so I have A of t squared eta squared. P A of t squared eta squared, and t phi phi is the same thing with the sine squared of theta. P A of t squared eta squared sine squared theta. And the other components vanish, right? There are no mixed components. If the two indices are different, this gives 0, because both of them must be t, equal to t, and the metric is diagonal, so this also has no off-diagonal elements. So we have this equation, this condition. Okay, and now we can discuss this component by component. It's not quite as bad as you might expect. It's only 2 components which have to be discussed, namely the TT and the eta eta component. So the TT component of the field equation. So I write this equation now with mu and nu equal to t. So then I have on the left-hand side RTT. This is minus 3 A double prime over A. I allow myself to drop the arguments now. And then I have minus R half GTT. Minus GTT is plus C squared with the 1/2. And now comes as a Ricci scalar, which I've written here. The Ricci scalar is 6 over C squared A or A squared. And then this curly bracket, C squared K plus A prime squared plus A double prime. And then minus lambda GTT, and GTT is minus C squared, so I get a plus. No, sorry, that was a plus. In the field equation is a plus. Nonsense. In the field equation I have plus lambda GTT, and GTT is minus C squared, so I get a minus. And on the right-hand side I have kappa TTT. Kappa, what was TTT? I've just calculated it. It's mu C to the 4. Okay, and I now strongly hope that the double prime term goes away. Yes, that's true. C square cancels, this gives a 3, and here I have a minus 3. So this term goes away in comparison to this. Okay? And then it becomes comparatively simple. So I have 3 C squared K over A squared plus 3 A prime squared over A squared minus lambda C squared is kappa mu C to the 4. This is the first equation we get. And I will discuss it in a minute together with the second one we get. The second one comes from the eta component. First, let me check if I got this correct, because if a sign is wrong, then I will get problems later. C squared A squared plus 3 over A squared prime minus lambda C squared. Okay, that's fine. So eta component. This begins with this term here. 1 over 1 minus k eta squared, 2k, 2 over c squared, a prime squared, a squared over c squared, no squared, a double prime. That's r eta. And then I have minus g eta half. Minus g eta half. So this is minus a of t squared divided by 1 minus k eta squared and the 1/2. And times r. Where's r? Here's r. 6 over c squared a squared, c squared k plus a prime squared plus a double prime. And then I have plus lambda g eta. G eta is a squared over 1 minus k eta squared. And on the right hand side I have kappa t eta. Here I forgot the pressure. I forgot the pressure here, yeah? This is just a squared over 1 minus k eta squared, but of course it must come with a pressure. So this is kappa p a squared, yes, over 1 minus k eta squared. And now you see this is very nice because all the terms with the eta go away. I can multiply with this denominator and then there's no eta. So both equations are just differential equations for A. They do not involve the eta, and of course they do not involve the angles because of the isotropy. So they're just differential equations for A of t. This can be simplified a little bit. So let me see. Here I have 2k, and here I have minus 3k. This is minus k. Here I have 2 over c squared a prime squared minus 3 times the same term, so it's again minus 1 a prime squared over c squared. And then I have plus 1 minus 3 times this term. So it's minus 2. And the last two terms are what they are. Can't do anything with this. Kappa p a squared. This is the second equation. So what we have in the frames here is what one calls the Friedmann equations, or the generalized Friedmann's equation. Let's call this F1, that is F2. Actually, Friedmann in his work concentrated on the first equation. He was concerned with the dust. And for the dust, yeah, the second, as we will see, the second equation is in a sense that it plays a less important role. But nowadays it's common to call both equations Friedmann equations or generalized Friedmann equations. Well, what do they tell us? First of all, they tell us that our ansatz always works. Yeah? I forgot to say something about the other components. All other components are then also true of the field equation, I mean, all components. So they don't give anything else. Actually, you might already have guessed this, because the phi and theta components are proportional to the eta component. And the same is the case here. If you look at, if you compare these two expressions, t theta, t theta, t phi, you see that they also differ just by exactly the same factors. So for this reason, they give exactly the same equation as the eta component. Yeah? So all three spatial components give the same equation, namely the second Friedmann equation. And the mixed components are just the equation 0 equals 0, which of course is true. Yeah? So you don't get anything else from the other components. So we have to discuss these two equations. What do they tell us? They do tell us that it always works with a perfect fluid. Namely, you give me any Robertson-Walker spacetime, your favorite Robertson-Walker spacetime. You choose a little k, you choose an a of t. You may choose whatever you like. Then I choose a lambda. I'm also completely free to choose lambda, a constant lambda, as I like. Then the left-hand sides of these two equations are determined. I can calculate them. And I just say, this is my mu and this is my p. And then the equations are satisfied. Yeah? So the equations are always satisfied. The equations for a perfect fluid are always satisfied. What is not satisfied is that mu and p are necessarily positive. In general, they will not be everywhere positive. And what is not satisfied is that they are related by an equation of state. Yeah? When we talk about perfect fluids, we usually require that between mu and p there should be a certain relation. They should not be completely independent. They are related at one point by one relation and by another relation at another point. Usually we don't want to have this. They should be related universally. And this is not guaranteed in general. But with these two reservations, we can say it's always true that the field equation is satisfied with a perfect fluid. So let me write this. So the field equation is always satisfied. All components of the field equation is always satisfied for a perfect fluid for all Robertson-Walker spacetimes. But mu and p are not necessarily positive. Actually, we will have to discuss what we have to make of, in particular, of a pressure which is negative. If we should consider this to be physically acceptable or not, we will discuss this in some detail. It has something to do with dark energy, right? Dark energy has a negative pressure. We will come to that. Mu and p are not necessarily positive, and the second result, mu and p are not in general related by an equation of state. Okay, so that's the general part. Also, one should note that because the left-hand side is a function only of t. In both equations, the left-hand side depends only on t, right? There's no eta, no theta, no phi. For this reason, also the mu and the p, of course, can depend only on t. Yeah? So they are constant on each slice, which is very natural. And with this information, it's clear that the Euler equation is automatically satisfied. It gives no additional information. And remember, the Euler equation says that the acceleration of the fluid lines is proportional to the gradient of the pressure. So the spatial gradient of the pressure, the gradient perpendicular to the fluid flow. But if this derivative is 0, and if the particles are moving on geodesics, as you hopefully remember, is true for this observer field. Yeah, this is geodesic in a Robertson-Walker universe. So the Euler equation just says 0 equals 0. So it doesn't give any additional information. Actually, should not come as a surprise because the Euler equation is a consequence of the field equation. Yeah? It cannot give additional information. So we will not talk about the Euler equation because it doesn't give additional information. Okay, so what do we do now? Well, we will discuss particular solutions to the Friedmann equations. And as I said, one usually wants to have not mu and p to be anything, but to be related in a certain way. So one wants to specify an equation of state. And if we do this, then we actually have to solve a differential equation for A. So if you give me some assumptions on mu and p, you say they should satisfy certain relations, then it becomes a coupled system of differential equations for A. And if this can be satisfied or not, that's a question we have to discuss for each case separately. And what I will discuss, the equations of state in quotation mark, which I will discuss, is the simplest one, of course, vacuum. I begin with vacuum, where both mu and p are 0. Then I'll do the dust. That's the original Friedmann work, this 1922 paper, and 23, the second one. And then I will discuss the perfect fluid for some particular equations of state. So that's a program for the next, I think, at least two lectures. And let's begin with the vacuum. You may ask, why do we do vacuum? We are interested in cosmology, and maybe we don't know very much about our universe, but we know for sure that it's not a vacuum. Yeah? So there are galaxies around and any kind of matter. So a vacuum solution doesn't sound particularly realistic. Well, first of all, it is advantageous to have the vacuum solutions out of the way to discuss them first, because just because we would like to know something about them. And actually, at least some of them do occur in relation with cosmology in a limiting sense. So certain class of solution tends towards vacuum solutions asymptotically, in particular to one particular vacuum solution, the de Sitter solution, which we will discuss in a minute. And for this reason, it's very good to know the de Sitter solution. Actually, it plays a very important role in cosmology, although it is a vacuum solution. It plays a role as a certain limiting solution. So that's the reason why we'll discuss the vacuum solutions in some detail. And also when the initial singularity is approached, at least for some classes of spacetimes with an initial Big Bang singularity, one can show that the influence of the matter becomes negligible if the singularity is approached. This is this was part of this work of the Russians, Belinsky, Kalatnikov, and Lifshitz. So there are a lot of things is done actually with vacuum solutions. Okay, so let's begin with vacuum. So my claim is that for vacuum, so this means mu equals 0, p equals 0. For vacuum, my claim is that we can forget about F2 because it's a consequence of F1. So I will prove this. So my claim is so when we solve the field equation for vacuum, we only have to solve F1. F2 is a consequence of F2, of F1. I will prove this. So if I write down F1 for vacuum, and let me solve this for the derivative A prime. So F1 implies obviously, oops, that's what I mean. that a prime squared is what? So I take everything else to the other side. So I multiply with a squared over 3. And then what do I get on the other side? On the other, this is 0, mu is 0. Yeah? So I get on the other side 3c squared k over a squared. But this comes with a minus sign. I take it to the other side, right? And this becomes a plus lambda c squared. Oops. From this equation, I can calculate the second derivative by, this can be simplified, of course. So if I multiply this out, I get minus c squared k plus lambda over 3 c squared a squared. If I differentiate this, then I get 2a prime a double prime. This is 0, the derivative, because it's a constant. And then I have lambda 3 c squared 2a a prime. Well, generically, a prime is not 0. One should have to discuss the zeros maybe separately, but generically it's non-zero. So let's divide by, not the a, the 2. Oops. And this gives us a double prime. And now my claim is, if I insert this expression into the left-hand side of f2, then I get the 0. So f2 is then automatically satisfied. So let me see, what is the left-hand side of f2? Left-hand side of f2 is minus k minus a squared over c, a prime squared over c squared, minus 2a a double prime over c squared plus lambda a squared. And I want to prove that this is 0. Yeah? I want to prove that this is 0. And here's all the information I have about a prime and a double prime. So let's insert these expressions. So that's minus k minus a prime squared over c squared. A prime squared over c squared is plus k minus lambda third a squared. Yeah, that's this term. And then I have minus 2a over c squared times a double prime. And a double prime I've just calculated here. Lambda third c squared a. So you see the k goes away. I messed up some factor somewhere. Where did I do this? This should be 0. Wait a minute, I forgot this term. I haven't written this term already. Yeah? So this, and now I have minus 1/3 minus 2/3 is minus 1, plus 1 goes away, everything. And this also, of course, cancelled. So I have this as this, and this is just our equation f2. So it is 2. Yeah, so we can forget about f2. It's automatically satisfied if we solve f1. And yeah, there are 3 cases now we have to distinguish. Namely, the lambda is a constant. It can be positive, it can be negative, it can be 0. This gives 3 different cases. And we I wrote a there, let me write 1 here. So let's begin with lambda equals 0. Yeah? So the vacuum solutions for lambda equals 0. Do you know a vacuum solution for lambda equals 0? Which maybe even happens to be a Robertson-Walker spacetime. Yeah, Minkowski spacetime should be in this class, right? So if we don't get Minkowski spacetime, we have made a mistake. Let's see if we get it. And let's see if we get something else. This is not clear from the outset, if maybe there are more than just Minkowski space. So if for lambda equals 0, so then we have the equation f1, how does it look like? So on the right-hand side, we have the 0. The lambda is also 0. So we just have 3c squared k over a squared plus 3a prime squared over a squared. And the lambda is 0, and the right-hand side is 0. So that's it. So we can, of course, cancel the 3, and we can cancel this. A is bigger than 0, so we never have zeros in the denominator. And then we have just the equation c squared k plus a prime squared is 0. And now we have to distinguish some more subcases. The k can take 3 values, right? Can be +1, 0, or -1. And we have to discuss them one by one. So let's assume k is +1. Then I have here something which is strictly positive, and here is square. So you see this doesn't work. Yeah? Because of course the scale factor should be real. Yeah? We don't want to have an imaginary scale factor, so we have no solution. So there are no vacuum solutions with lambda equals 0, which have positive spatial curvature. And let's say k equals 0. K equals 0 gives a prime squared equals 0. This means a is a constant, right? If the derivative is 0, this means that a is a constant. So a of t is a constant. Let's call it a naught. And yeah, what is the metric then? Let's insert this into the metric. The metric was minus c squared dt squared, and then comes the a of t squared, which in this case is just a constant. And then I have d eta squared. In this case, k is equal to 0, so there's no denominator. Yeah, it's 1 minus 0 plus eta squared, d omega squared. Do you know this metric? Well, maybe it's helpful to make a coordinate transformation if we transform from eta to r by setting r equal to a naught times eta. Yeah. This is a length. This is dimensionless, so r is now a length. And then the metric is minus c squared dt squared plus dr squared plus r squared d omega squared. I think now it's obvious that this is Minkowski spacetime. Yeah? Minkowski spacetime in spherical polars. Yeah, the spatial coordinates are spherical polars. And yeah, the slicing, the surfaces, hypersurfaces t equal constants are precisely the synchronous surfaces for inertial observers. Yeah? So this is just standard Minkowski spacetime, Minkowski space in standard coordinates. So here we have x, y, z. This is the r coordinate, which is made out of these x, y, z, and the slices are just this here. And of course, this is a vacuum solution with lambda equals 0 and k equals 0. Yeah? And what we have found out, what is not trivial, maybe not quite trivial, is that it is the only one. Yeah? Because we don't get any other solution if we have lambda equals 0 and k equals 0. Okay, then the third case we have to discuss is k equal minus 1. So k equal minus 1, then I have 8 prime squared is c squared. Yeah? I take this to the other side. It's on this side with a minus sign, so on the other side with a plus sign. So this works. Positive, positive. I can solve this. So of course the solution is a of t is c times t plus integration constant, which is irrelevant. We can always shift the 0 of our time axis to any point we like. Yeah? So you may put here, instead of t, you may write t minus t0. You may choose any t0 you like, but there's no reason to introduce this. And then the metric is dt squared plus c squared t squared. So now we are in the case k equal minus 1. So I have 1 minus minus. This gives plus eta squared plus the angular part. Do you know this metric? We had it already on the board, actually. You saw? You forgot the name, but you remember that we had it on. The name was Milne. It's named after Edward Milne, and that's also Minkowski space. But Minkowski space in different coordinates. Yeah. Actually, if you want to prove this, that it is Minkowski space, then you can make a coordinate transformation. Let me see that I get the factors wrong. The factors right. What do we do? So. This is Minkowski space yeah, in Milne representation or Milne coordinates or whatever you like to call it. So if you want to verify that this is in fact Minkowski metric, you should find a coordinate transformation which takes it to the ordinary form of the Minkowski metric. So let's write the ordinary form of the Minkowski metric. Now I cannot call the time coordinate t because I've used the t here for something else. So let's call this tau. And then we have what do we have? Which representation do I use? Yes, the polar coordinates. Yeah. Yeah, that's Minkowski spacetime. And now I have to tell you how the tau and the r are related to t and eta. Or let's use the representation with the chi. Maybe that's nicer. Minus c squared dt squared plus c squared t squared. You remember we had three different representations for the spatial part of a Robertson-Walker universe, the one with the eta, the one with the chi, and the one with the rho. We can rewrite this in terms of the chi. Then we have, this is k equal minus 1, so the eta is as a hyperbolic sign. Square of chi, d omega squared. Yeah? So that's exactly the same thing. It's just a space of constant negative curvature either in this representation or in this representation. And now I have to tell you how the tau and the r are related to the t and the chi. And the relation is c tau is, let's do it without the, it's t times hyperbolic cosine of chi. And r is, here I need the c, just for dimensional reasons. The same thing with hyperbolic sine. So let's check that this is true. So we get d tau is cos chi dt plus t sin chi d chi. And the r is the sin chi dt plus ct cos chi d chi. And now let's insert this into the metric. So then I get minus c squared, this here squared. This here squared is cos chi dt squared. Then plus the mixed term. I don't write the mixed term, but please keep it in mind that there is a mixed term. Plus t squared sin squared d chi squared. And then from this term, dr squared, I get plus c squared this squared, chi dt squared. And now I get again the mixed term. It's the same mixed term. Yeah, if you multiply this with this and this with this, you get the same thing. But here you have a minus sign. Here you have a plus sign. So the two mixed terms go away. That's why I didn't write them. Plus c squared t squared cos squared d chi. And then we have the angular part, the r squared d omega squared. This is c squared t squared sin squared d omega squared. Oops. And now let's collect everything together. I have minus cos squared plus sin squared. This is minus 1. So I get minus c squared dt squared. Then I have minus sin squared plus cos squared. This gives plus 1. Plus, oh, this is 1c. This is spurious, right? So I should write it only once. So this is plus c squared t squared d chi squared. And then the angular part plus c squared t squared sin squared d omega squared. And if you compare with this expression, have I done it correctly? Yeah, I think everything is fine, right? So this is in fact the same metric which we have found here. So it is indeed Minkowski space. It is Minkowski space, but in these new coordinates. And yeah, these coordinates do not cover the whole space. Because you see that here, for instance, you see that that something goes wrong as t becomes 0. because this coordinate transformation, yeah, this becomes bad if t becomes 0. Then it's not allowed coordinate no allowed coordinate transformation. And if we have here our ordinary coordinates, let me now denote a tau. It is this tau here. Then you see that t equals 0 is just this point here. And the other surfaces t equal constants are these hyperboloids. And the t lines, the lines which are orthogonal to these hypersurfaces, are these straight lines. So that's the Milne model. So it covers only the future light cone of one event. It's not all of Minkowski space. And it slices this space-time into hyperboloids, into spaces of constant negative curvature. Yeah, on this space, the metric is positive definite. It's a Riemannian manifold, three-dimensional Riemannian manifold, and it has constant negative curvature. So we have sliced part of Minkowski space into hypersurfaces with k equal -1. And that's it. That's all solutions. We have now discussed all possible cases with lambda equals 0. So the vacuum solutions with lambda equals 0, which are Robertson-Walker spaces, are just Minkowski space in two different representations. There are no other ones. And in particular, we have seen, which maybe you have expected it, but it's maybe not quite trivial, that it's impossible to do it with k equal +1. Yeah? So you can slice Minkowski space or part of it into flat slices. You can slice it into negatively curved hyperboloids, but you cannot slice it into positively curved spaces. This has nothing to do with topology. It's just about local differential equations. Yeah? So it's not even in an arbitrarily small neighborhood. It's possible to get slices which have constant positive curvature in Minkowski space-time. Okay, that's lambda equals 0. We have done it. There's another board. So the next case is, let's do lambda bigger than 0 now. I'm sorry?
What is the de Sitter solution?
This is de Sitter. We will come to it. This is de Sitter. Yes, exactly. No, it's not B, it is 2. Yeah, this, as I said already, this is an important space-time which plays an important role in cosmology, and we will spend some time with this, probably also the next worksheet. So this is what we call de Sitter solution. But again, we have to, so what is the equation we have to solve? I have it here. Oops. F1, where's F1? There in the frame, here. That's the equation now with the right-hand side is 0 and lambda is positive. So the equation we have to solve, write it down, let me write it down again, is, should I divide by this? I'll write it as it is there. 3c squared k over a squared plus 3a prime squared divided by a squared minus lambda c squared. That's the equation we have to solve. Yeah, that's F1, the Friedmann equation for this case. And we do it with a positive lambda, and again we have to distinguish three cases. K can be +1, -1, or 0. So let's begin with the case k equal +1. K equal +1. Then I have what? I have 3a prime squared over a squared. Let's take this to the other side. Lambda c squared, and k is +1, so it comes on the other side with a minus sign. 3c squared over a squared. That's a differential equation. Let's try if we can solve this differential equation. So a good idea is to solve for a prime. So a prime squared is a squared over 3 lambda c squared minus 3c squared a squared. And I think I multiply this out, or do I? Maybe I pull the c squared out of everything, and then I have lambda third times a squared, and here I have -1, right? yeah, the 3 goes away, the a squared goes away. It is just this. Okay, this means a prime, this is dA by dt, right? That's a shorthand notation for this. So we have dA, if I take the square root out of both sides, I have lambda third a squared minus 1. And on the other side, I have plus minus c dt. That's what we have to integrate. And lambda is positive. This is important. Yeah, this is important. So I can write integral signs in front of both sides. And yeah, you could look this up, of course, but I think I can do it with a substitution. And it's important that this is positive, because it wouldn't work if lambda is negative, right, with a minus sign here. So what do we substitute if we want to get rid of such an expression? So a good idea is to write this lambda third square root out of this a as minus 1, so I should substitute this as the hyperbolic cosine. Because cos squared minus 1 is sinh squared. Yeah, so this is a good substitution. Then I get dA is root 3 over lambda sinh u du. And I can insert this into my differential equation, or my integrated version of the differential equation. Root 3 over lambda, dA is this here, sinh u du. And this here is square root of cos squared minus 1. And you see that's very nice, because this is precisely the sinh. Yeah, so this goes away. And on the right-hand side, I have just plus minus c integral dt. And yeah, even I can integrate this equation, yeah, because everything is constant under the integral. So I have root 3 over lambda u is yeah, plus or minus ct. Again, we can introduce an integration constant. So we could write, instead of t, you could write t minus t naught, but this is just about shifting the origin of the time axis as you like. And now we have found our a of t. What was our substitution? A was root 3 over lambda times cos. Oops. Root 3 over lambda times cos. And we have calculated what the cos is. Under the cos, the plus or minus sign doesn't matter, because cos of plus something is the same as cos of minus is. So I can forget about the plus minus sign. And I just get, this comes to the other side, so I have root lambda third ct. That's the solution. That's our scale factor. And the metric, well, what is this? How does this look like if we plot this? So we see t runs over all of R. That's not, it's not always the case. Remember, in Robertson-Walker universe, we usually have to be aware of the fact that it might start at a finite time and maybe also end at a finite time. Yeah, we have these times which are denoted ti and tf. But here, ti is minus infinity and t plus is plus infinity, because this is everywhere positive. So we have the full time axis, and yeah, the cos function looks something like that, right? So it's a universe which is contracting, reaches a minimum, here with our choice at t equals 0, and then it starts expanding again. Yeah, so it comes together and it expands. And it is a space, it's a universe with k equal plus 1. So the spatial sections are positively curved. So their natural topology is that of a sphere. Yes, a 3-sphere. So we have a 3-sphere coming in from infinity, infinitely in the beginning, infinitely large. It's contracting, 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 reaches a minimum, and then it's re-expanding again. And symmetric looks like that. Symmetric is minus c squared dt squared. This is a scale factor, so if I square this, I get 3 over lambda cos squared root lambda over 3 ct. And then it's a space-time with k equal plus 1, so I have d eta squared 1 minus eta squared plus eta squared d omega squared. Yeah, and this is what one calls the zeta universe. It was found as a solution to Einstein's field equation with a positive cosmological constant by there's an R missing, by the famous Dutch astronomer Willem de Sitter, who also in later years played an important role in the development of cosmology. Later he wrote a paper together with Einstein where they invented what is called the Einstein-de Sitter universe. That's something different. Yeah? De Sitter universe is something different from Einstein-de Sitter universe. Einstein-de Sitter is what we have on the next worksheet, what we will discuss there. This is the dust solution, not a vacuum solution. So the de Sitter universe is a vacuum solution with a positive cosmological constant, and that's one form of writing it down. And from this form, we see quite clearly what the geometric behavior is. I've already told it. So it's contracting and then re-expanding. So you may represent it in the following way. At a certain time, t equals 0, it has its minimum radius. So that's a three-sphere, what I've drawn there. And then in the course of time, it expands. Up to t to infinity. And if I go to the past, then it also expands symmetrically. So this is for t to minus infinity. And at each point I have, each point in time, I have such a three-sphere, which is the universe. And the standard observers, of course, are these geodesics, which are perpendicular to these slices. So that's the de Sitter universe. Actually, I've drawn it. It looks like a hyperboloid, right? And actually, it is a hyperboloid. It really has a strict geometry of a hyperboloid, but I should say a hyperboloid because it is in 4 dimensions. Yeah? It's a 4-dimensional thing, a space-time, not a Riemannian manifold. It has Lorentzian signature. It is a 4-dimensional Lorentzian manifold which can be embedded into 5-dimensional Minkowski space. Yeah? And as that, it is a hyperboloid. And actually, let me write this down. And if you're interested, I can also give you the coordinate transformation, the representation, which to prove this. But I will not do this on the board because it is a little bit boring, and I don't want to waste my time with that. Where is the transformation? Oops. Oops. Here I have it. So
T is 0 and C.
Yeah, of course. Yeah. This was supposed to be a 0. Was not quite. Didn't make the full circle. Okay. So my claim is that this universe can be embedded into 5-dimensional Minkowski space, and that it is then represented as a hyperboloid. So embedding of the Sitter universe into 5-dimensional Minkowski space. So what is 5-dimensional Minkowski space? It's a metric. Well, it's 5-dimensional, so let's write it this way. It is the x squared plus the y squared plus the z squared. How do I call it? W? Yes, W. I need a 4th spatial coordinate. Let's call it W, and then I have a time-like coordinate, which I call V. Yeah, that's 5-dimensional Minkowski space-time, and it is a hyperboloid. 4-dimensional hyperboloid. So this is x squared plus y squared plus z squared plus w squared minus v squared is lambda over 3, right? No, 3 over lambda, of course, the other way around. Yeah. So what is the dimension? If you are not sure if it is 3 over lambda or lambda over 3, you can always make it become clear by looking at the dimension. What's the dimension of lambda? Think of the field equation. What's the dimension of lambda? It's not dimensionless.
1 divided by an area.
I'm sorry?
1 divided by an area.
by an area. Here's 1 over area, or 1 over length squared. Yeah, that's the dimension of lambda. So there's associated with the lambda, there's a length. And the length, of course, is the curvature radius. Yeah? And big lambda means that this length is small. So big lambda means small curvature radius. And you see, therefore, it must be 1 over lambda, because here I want to have something like a radius squared. Yeah? So this is the way in which it can be represented. And if you want to verify that, in fact, you get this as a metric induced on this submanifold. Yeah? This is a 5-dimensional space with a metric. This is a 4-dimensional submanifold in this space. Yeah? If I have one equation which connects the coordinates, I get something with codimension 1. And codimension 1 in 5 dimension means it's 4-dimensional. And my claim is that this 4-dimensional submanifold is a de Sitter universe. So the claim is that on this submanifold, this is the induced metric. So I have to tell you what is the relation between my T and, oh, here I've used eta. Would you allow me to change this into the chi representation, which is completely equivalent, because then I can use, this is k equal plus 1, so I have a sign here, sine of chi, the omega squared. Yeah? So that's the same thing, just represented in these other coordinates. I have forgot the, no, it's correct, it's correct. So I have to tell you how are these coordinates, t and chi, and the angles, here theta and phi hidden, how are they related to these capital letters? And the claim is a v. Yeah, the v is just the scale factor. It's a scale factor. Yeah, so the scale factor goes in this direction. This is the v direction. Yeah. The other 4 directions are the space-like directions. Here plus, 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 plus. And the v direction is a time-like direction. This goes up in this diagram. And in this direction, the scale factor changes. And the scale factor is just proportional to v. So this is root 3 over lambda. No, sorry, no, what I said is not quite true. It cannot be quite true because the scale factor is not monotonic, right? But the scale factor is uniquely related to v, that's what I meant. But it's not exactly the same. You see, this decreases and then increases again. The v should increase along the whole axis, so it cannot be the same thing. Yeah? And one is a cosh, the other thing is a sinh. So it's a sinh of the same argument, root lambda over 3 ct. And the w is root 3 over lambda cosh, root lambda over 3 ct times cosine of chi. And yeah, the spatial axes are root 3 over lambda cosh ct, and now with the sine of chi. And then the two-sphere part, where theta and phi are the coordinates. And the x usually comes with cosine phi sine theta. The y, here the same expression, here sine phi, sine theta, and the z, same expressions, and here cosine theta. Yeah? So if you assume this coordinate transformation, this representation. First of all, you verify that this defines a manifold where this identity holds. Yeah? So if you add this up, x squared plus y squared plus z squared plus w squared minus v squared, you get 3 over lambda, if I wrote everything correctly. So this should be an identity. So you really parameterize this submanifold. And then you calculate the differentials, dx, dy, dz, and so on, plug them into this expression. And because you have expressed it by 1 coordinate less, by 4 coordinates in a 5-dimensional space, you get something induced on a 4-dimensional manifold. And the metric which you get, if you plug the differential of these expressions into this, is precisely this here. Yeah? So this demonstrates that it is really this hyperboloid in 5-dimensional Minkowski spacetime. So I did the calculation in detail on the board for the 2-dimensional Riemannian hyperboloid. Yeah, of curvature k equal -1 into 3-dimensional Minkowski space. And this calculation is quite analogous. You just have a few extra dimensions. Yeah? And well, of course, it is analogous, but there's an important difference. The important difference is the signature. Yeah. What we did earlier was we had a Riemannian manifold, and we embedded it into Minkowski spacetime. So the additional dimension was the time-like dimension. Here we have a Lorentzian manifold. We embed it into Minkowski spacetime. So the additional dimension has a space-like character. Yeah, that's the difference. So as far as the signature is concerned, it's different. But apart from this, the calculation is quite analogous. So if you have 20 minutes or so to spend, then you can easily do the calculation for yourself. So what else can be said about the zeta universe? As I said already, it's an important space-time. It plays an important role in modern cosmology. It, as we will see, it has something to do with the steady-state universe. It has something to do with inflation. It has something to do with dark energy. So it is an important space-time, and we will come back to it fairly often. And for this reason, I want to discuss it a little bit further. So first of all, let's look at the horizons. Are there horizons in this space-time? So what do we do in order to check if there are horizons? There's a strategy. We have discussed this in general for a while, I think 2 weeks ago or so. And in the worksheet for this week, we will do it with the Einstein de Sitter universe. We will discuss the horizons there. So what is the strategy? If you want to check if there are horizons, what would you do? What is a strategy to find this out? Don't remember? Well, the important catchword is conformal time. Yeah? Introduce the so-called conformal time. And if this runs from minus infinity to plus infinity, then you know that there are no horizons. If it does not run from minus infinity to plus infinity, we have to look a little bit careful, because you might have compact spatial sections, and it's not so easy. It's not automatically clear that there are horizons. But in any case, you get the important information for it. Maybe maybe I should ask another question first. Does this have a big bang or a big crunch? So that's what can be read directly from this representation with a proper time t. Yeah? If this runs from minus infinity to plus infinity, and that's what it does here, then there's no big bang and no big crunch. Yeah? So instead of coming together in the past or in the future, actually the world lines are very strongly diverging from each other. Yeah? So it's the exact opposite of a big bang and of a big crunch. And, but the horizons cannot be directly read from this expression, because the fact that t runs over the whole real line doesn't imply that also the conformal time runs over all of the real line. So we have to introduce a conformal time. I called it capital T, which maybe is not a very suggestive notation, because it does not have the dimension of a time. Yeah? Ct is dimensionless. So T, the conformal time, has a dimension of an inverse velocity. And it was defined by this relation. This is dt over a of t. So let's see what this is. So this is, in our case, this is a cosh function in the denominator. So this is root, no, the other way around, 3 over lambda, cosh root lambda over 3 ct. Okay, can you integrate this? Do you know by heart what this is? Well, I do not. I looked it up somewhere. Probably, well, I think I could do it with a substitution, but I was too lazy for doing it myself. I looked it up. So this is, here it is. It is, let's write a C in front of everything. Then this is dimensionless on the left-hand side, yeah? Then this is dimensionless. And here it's nice, because here I have C times this root, and here I then also have C times this root. So then it's convenient. So it is the Arcus sign of the hyperbolic tangent. Tangent root lambda over 3 ct. And then you are, of course, free to add an integration constant. And in this case, the usual convention is to put a minus pi half here. That's a convention, yeah? It's just about shifting the origin of the time axis wherever you like. This is convenient because then I have the sine of ct plus pi half is equal to the hyperbolic tangent of this root times ct. And where the sine of something plus pi half is a cosine, right? So this is a cosine of ct. Now you see, what's the range of the hyperbolic tangent? So if t runs from minus infinity to plus infinity, what does the hyperbolic tangent do? You know, hyperbolic tangent is this. Yeah? So it goes from minus 1 to plus 1. So if t runs from minus infinity to plus infinity, this tangent here, hyperbolic tangent, runs from minus 1 to plus 1. This means we can choose an interval where whenever this becomes 0, the space-time is gone. Yeah, it's destroyed. So we have to choose an interval where this is non-zero and actually positive. Yeah, and sorry, not positive. It runs from minus 1 to 1. So we'd have to choose an interval where the cosine runs from minus 1 to 1. I think that's the interval from minus pi to 0, right? So we can say that ct, which is dimensionless, runs from minus pi to 0. So that's finite. Yeah, the finite. So the t interval is infinite, no Big Bang, no big crunch, but this is infinite. So we have to be aware of the possibility that there are horizons. It depends on what the chi-coordinate does. Yeah, if it is restricted to a compact range, or if it can run out to infinity. So let's plot this conformal diagram, where we plot ct on one axis and the chi on one axis. So, oh no, this is I shouldn't put it here because this is negative with this choice. It's a common choice. More or less everyone does it in this way. Of course, you could choose a different interval, yeah? Just any other interval where the cosine runs from minus 1 to 1. So I have here 0, and I have here minus pi. So the conformal time is restricted to this interval. And what about the chi-coordinate? We are in a space-time with k equal 1, yeah? Positively curved. And in a positively curved space-time, the natural topology of the space is that of a 3-sphere. And the chi-coordinate runs from 0 to pi. So this is the north pole, chi equals 0, and chi equal pi is a south pole. Here is pi. So our space-time is restricted to this. Actually, it's the square. Yeah, this has length pi, and this has length pi. So I should draw it as a square. Sorry. That's about a square, right? So that's it. Here's our space-time. So this is the south. This is the north pole, right? So here we are on our spheres. It's our S3 sphere. Here is chi equals 0. This is chi equals 0. And then chi runs from the top to the bottom. Here is chi equal pi. This is the south pole. And here's the equator, chi equal pi half. Okay, now what about horizons? In this diagram, the conformal time is made in a way that light rays run under 45 degrees. Yeah? Ct and chi are both dimensionless, and they are related in the way that radial light rays run under 45 degrees. And now you see, yeah, these are light rays. I shouldn't have shaded this. So what do you say? Are there horizons or are there no horizons? Remember, there are two notions of horizon. The first was an event horizon. Fix an event, and the question is, can all standard observers be seen at this event? What do you say? Can all standard observers be seen? Obviously not. Yeah? There is a horizon. Yes, this is a particle horizon of this event. And if you approach the end of the world, The end of the world is at Ct equals 0. If you approach the end of the world, which means if you go up in this hyperboloid, then in the limit you see the whole world. Yeah? The only point which actually never comes into sight is the antipodal point. There's this chi equal pi. This will never be seen. It will be seen at time little t equal infinity, which corresponds to Ct equals 0. But apart from the South Pole, you can see any other standard observer if you wait long enough. And similarly, if you ask about the event horizon of this particle, then you see again there is an event horizon. So there are events which this particle will never see, namely this events here and these events here. So there are event horizons and particle horizons. So event horizons and particle horizons exists. Okay, this was a little bit about the zeta universe. We will come back to it later. Actually, we will come back to it very soon, and then also in one of the worksheets. But for the time being, that's all what I want to do with this representation, where we have this, these positively curved time slices. So I try to clean the board. And then we can consider the case k equal 0. Let me remove this here. So we don't need this. Okay, so we are discussing vacuum solutions with lambda positive. It's still written up there. And we have discussed the case k equal plus 1. So let's now do the case k equals 0. K equals 0, where the differential equation is up there. Now I set k equal to 0, then it becomes considerably simpler. 3a squared over a squared is lambda c squared. And lambda is positive, so this is nice, because we have positive quantities on both sides of the equality sign. So let's see if I can integrate this. So I get dA over a is root lambda over 3 times c dt with a plus minus, right? That's it. And that's even easier to integrate than what we did before. So this is just the log, right? This is ln a. This is plus or minus root lambda third c t. And again, you are free to add an integration constant. So you may write instead of t, t minus t naught. So we have a of t is the exponential function with a plus or minus factor, lambda 3 ct. So there are two solutions. You see, one is expanding, one is contracting. Yeah? And one obviously is exactly the time reverse of the other. So actually it suffices to study one of them. We get the other one just by replacing t with minus t. Here we just let run the time backwards, and we get the other one. So choose the plus sign. So the minus sign is just the time reversed situation. And then the scale factor looks like that. It is exponential growth. Yeah? And the metric is minus c squared dt squared plus e. I choose a plus sign, so I have plus 2 root lambda 3 ct. And then the angular part, the spatial part, the chi squared. This is k equals 0, so I have, with the chi representation, I don't have it anyway. And here I have chi squared, the omega squared. So what is this? Has anybody seen this metric before? Believe it or not, it's again the zeta. It's again the zeta, but in a different representation. Yeah? The zeta universe in a different representation. In order to prove this, I tell you again how you represent it in terms of the hyperboloid. Yeah? So I tell you again how you have to express the relation of the coordinates to the capital X, the capital Y, the capital Z, in order to get this representation, if I find it. Oops, where is it? Oh, come on. I'm fairly sure I brought it with me. It's something with a log. Ah, here it is. Here it is. Okay, that's a flat metric, right? That's a flat metric. We are in the case k equals 0. So I can also write this as the little x squared plus the little y squared plus the little z squared. And I tell you how t, x, y, and z are related to this capital X, Y, Z. So representation with the 5-dimensional embedding. Yeah. So for the old representation, the representation with this t, which is a different t than this here, with this t and this part here, the positively curved spatial part, I've written the relation here. The relation between the coordinates in the embedding space and the coordinates on the manifold. And the same I do now for this representation. And it is like that. It is t, or ct rather. Ct is root 3 over lambda, the log of root lambda over 3 w plus v. The little x is root 3 over lambda, the big X over w plus v, and analogously for y and z. and that is root 3 lambda z over w plus v. So if you introduce on the hyperboloid, which lives in the space where w, v, x, y, z are the coordinates, if you introduce on these hyperboloids these new coordinates and pull back the metric, the 5-dimensional Minkowski spacetime onto this submanifold, you get this representation. Again, I don't do it on the board, so you would have to calculate these differentials, right? The t squared, the x squared, the y squared, the z squared, and then see that it is just the pullback of the hyperboloid. So the interesting thing, what you see here is that this doesn't cover the whole hyperboloid. Because you see, under a log, you should have something which is positive. Yeah? Because a log is defined only on the positive numbers. So w plus v can take only positive values. And this means you don't get the full hyperboloid. What you get is the following. If you have here the hyperboloid, oops. Let me try if I can get a proper impression of what's going on. You get 1/2 of it. So you slice it here. And you get only what is on one side of this. And this is a boundary where the slices become light-like. The slices should become time-like on the manifold which is represented in this way. Yeah? Because here you have something negative, so t equal constant must be a space-like hypersurface. But if you approach the boundary, then it becomes light-like. So this is nice, all these things. So this is a slice through a hyperboloid. Try to imagine it. So these are the slices t equal constant in this representation. And it stops when you reach this light-like boundary, because then it cannot be done with it cannot be extended as a Robertson-Walker spacetime, because the slicing cannot be a space-like anymore. So that's the expanding version. Yeah, if you go in this direction, the whole thing expands. So there's a plus sign. Of course, you can also consider this here, then the whole thing contracts. Yeah, in the direction of positive time, this here contracts. It starts here and then contracts. So you can cover both halves, but you cannot glue them together on this line. Yeah, on this it's not a line; it's a 3-dimensional hypersurface. On this hypersurface, the whole thing goes awry. And you see, you can slice one and the same spacetime in quite different. Actually, we have seen this already with Minkowski spacetime, right? Minkowski spacetime, we had this inertial slicing and then the Milne slicing, which also gave us two different representations of the same spacetime, at least locally, in two representations which look completely different. Something similar we have here. And actually in this version, with this exponentially expanding scale factor, in this version it makes the de Sitter universe makes its occurrence in many applications to cosmology. So we will, if you remember, I mentioned this briefly when we discussed the Hubble constant. If the scale factor depends on time in an exponential form, like this here, then the Hubble constant is really a constant. It is independent of time. Yeah? So this is an example for a spacetime where the expansion, the rate of expansion is constant. And this was what was suggested by the steady state model in the 1950s or even late 40s. And for this reason, the de Sitter universe is also related to this idea of a steady state universe. And as I said, it's closely related to dark energy and also to inflation. So that's the second representation of de Sitter space we have. And then there's a third representation. I have 4 minutes. I think I cannot do this. So this is the one with k equal -1. So to give away the punchline, when we study the case k equal -1, we will also get de Sitter, but in the third representation. Yeah. But I will do this on Friday. And then I will study the case lambda smaller than 0, which is the so-called anti-de Sitter universe. But I will do this a little bit shorter because Well, in my personal view, anti-de Sitter is not so interesting. The string theorists are of a completely different opinion, but I'm not a string theorist. So I'm fairly sure that we live in a universe with a positive cosmological constant. And for this reason, I think de Sitter is much more important than anti-de Sitter. So any questions onto these two aspects of de Sitter which we have discussed today? If not, then I bring this to an end on Friday. Okay, see you on Friday.